All right. Good morning, good afternoon, everybody, depending on where you're dialing in from. And welcome to episode 4 of Technically Speaking, Maximizing Airflow Resources. I'm super excited today because we just about hit our maximum number of registrations for the episode today. So really excited that the Technically Speaking series has continued to be of interest. And we have a lot in store for the rest of the calendar year. I'll talk a little bit about that at the end of the hour. But today we're going to focus on maximizing the airflow resource. So just a couple of quick formalities and introductions for anybody who's joining us for the first time. My name is Brandon Burton, and I am the Vice President of Technical Application here at NextGear and CoreLogic, and also the chair of the ANSI ICRC standard. So I spent a lot of time talking about the technical side of our industry. And I'll share some contact information with you towards the end of the presentation today. But one of the things that I always like to say as I go into these is I love to hear from the industry about what types of technical issues and challenges you're having in industry. And I love to talk about those issues and bring them to the forefront and ensure our industry solves them. So please do stay in touch, not just through the webinar today, but any way that I can be of assistance to you and your mitigation business. So with that said, let's go ahead and jump right into things. A couple of quick formalities as I get into the overview. First of all, the chat section of Zoom is something that we don't use during the webinars. We instead use the question and answer tool. So as we go through the presentation today, if you have any questions on anything that we're covering, please drop those questions into the question and answer tool. And then at the end of the session, I'm going to go through a live Q&A period where we will answer all of those questions. Those of you that are here today with me in person live, you'll get that Q&A session. If you're going to watch this recorded after the fact, the Q&A is not a part of the recording. So just keep that in mind. I greatly appreciate those that are attending live, and that's kind of an added value we give to those that spend the time to join us live. So with that, let's jump into the topic, maximizing the air movement resources. I like this topic. Of all the topics that we're going to cover this year, I like this topic the most because it is by far, in my opinion, one of the most important assets that we deploy in a mitigation project. The most important asset is the personnel resource, but right beneath that is air movement. And it's often overlooked in terms of its importance and how critical it is to the mitigation process. So we're going to spend a lot of time today talking through a couple of different kind of elements of airflow, if you will. The first and most important being just the role and purpose of airflow. What does it do? Why is it there? Which will be a good review of some of the stuff that we've covered in the first 3 episodes of Technically Speaking. But we'll give a little more kind of flavor to that as we go through it. Then we're going to dig real deep into the IICRC S500 standard. I want to talk specifically about the calculation that the S500 standard provides in terms of the number of general air movers that are supposed to be deployed. From there, we'll get into some installation best practices. Just because we've got a certain number of air movers doesn't mean they're going to do a great job for us unless we understand how to deploy them. So we're going to get into some installation best practices. And there is a right way to install them, and there are several wrong ways to install them. If we're not using the air movers properly, they're not going to achieve the goal for us that we'll talk about in role and purpose. And then finally, I want to talk a little bit about specialty systems, things like inter-air drying systems and the like. We're not going to get super deep into specialty drying systems today, although I'm going to introduce the topic and we'll begin talking about some best practices there. Episode 7, a couple of months from now, we're going to get really deep into these specialty air movers. So mark your calendar. Let's see, today's May, so mark your calendar for July. If you do a lot of cavity drying, a lot of hardwood floor drying, and other specialty type installations, you're really going to want to attend that episode in a couple of months because we're going to dig pretty deep into that topic at that point. And then the last thing that we'll do today before we get into Q&A is we will talk about just some of the general secrets that we talked about today. So I'll kind of summarize things into the best kept secrets of air movement. Okay, so that's kind of an overview for you where we're going to go. Let's start with role and purpose. And just a quick reminder as I do that, don't forget to throw your questions into the Q&A as we go. That's a great place to log that question so that I make sure that I see it at the end of today's presentation. So role and purpose. What is the role and purpose of air movement? So in terms of a drying environment, right? Obviously, what we're trying to do is we're trying to remove excess moisture from the environment, not only to bring the building materials back to a normal moisture level, but we're trying to do that for a purpose, right? And that purpose is to prevent the damages that that excess moisture can cause, not only to what is wet, but the surrounding materials that can become secondarily affected. So there are different tools that we deploy to accomplish that goal, right? And some of those tools that we deploy are anything from air movers to dehumidifiers to heating systems, and even all of the the related tools like instruments and things like that that we use to understand where that moisture is and how it's responding. Air movement in that cycle of conversation plays a very, very specific purpose, right? And it's very basic, but it's extremely critical. To understand that role, let's take a really simple look at an affected area here in this schematic or cross-section of a building. If we had an area here that was affected, maybe a carpeted room and a living room or something like that over a crawl space, when we install something like dehumidification, which is removing moisture from air, it's adding some heat energy to the air, it's therefore producing some warm, dry air. The only way that that warm, dry air is going to be of any use to us is if we place that warm, dry air into direct contact with the wet evaporating surfaces. And this is where air movement becomes key, right? We install these air movers so that we can draw that warm, dry air from the environment and then move that readily and rapidly immediately across that wet surface. Now, in the previous episodes, you've probably heard me stress just how important that interaction at the surface is. And the key with air movement is exactly that. To validate whether or not air movement has been effectively deployed, the best way to do that is to use a thermal hygrometer. And we talked about some of these measurement principles in earlier episodes. The common mistake that a lot of us make is when we walk into an environment with a thermal hygrometer and measure temperatures and relative humidities, we're usually walking around the environment and we're measuring up here at chest height, right? Which is an important measurement, but that's not the air that's doing the work, right? The air that is several feet above the floor or away from the wet surface is not what's drying the surface. What's drying that surface is the air in contact with that surface. So a secondary measurement that's really critical is once you know what's happening up here at chest level, I need to find out what's happening down at foot level, right? What's happening right down there at the surface. And if there's any significant deviation there, if the air above is much warmer and drier and the air below is much cooler and wetter, your air movement installation has failed, right? And that's really how we validate an appropriate installation of air movement. It's not by taking one hygrometer reading, it's by taking multiple hygrometer readings and comparing those readings for any deviation. Now, we could make this argument from the chest level down to the floor. I could also make the argument from the left-hand side of a drying chamber to the right-hand side of a drying chamber, right? No matter which dimension we're talking, these readings should be relatively equal. And if they're not equal, then circulation is failing, the blending effect of air movement is failing. Now that's the simple, right? At the visible surface. What makes things even more complicated with air movement is the visible surface isn't the only surface where evaporation is occurring. And we have to fully understand, and here's another concept that we've talked a lot about this year. We have to fully understand not only what's wet at the surface, we have to understand how these assemblies are constructed, right? This wall assembly, how is it comprised? And how deeply did the water penetrate into that wall assembly? In terms of air movement, what that means is I need to understand what are the wet surfaces inside of these cavities. Is there water evaporating from those surfaces? And if that is true or possible, then we need air movement to evacuate the water that's evaporating inside those spaces as well. Every wet evaporating surface should have air movement removing that evaporated water and replacing that with the warm, dry air created by either dehumidification, ventilation, heating systems, whatever your humidity control resource is. And that's the phrase typically used in the S500 to describe that. Dehumidifiers being the most common solution, but not the only solution, right, for providing that humidity control resource. So that's kind of the high-level purpose of air movement. Let's kind of review some of those concepts. So warm, dry air must make contact with all wet evaporating surfaces, right? Warm, dry air in contact with the wet evaporating surface. That means I'm circulating the dehumidified air throughout the space, throughout the chamber, to all of these areas that are affected within the chamber. By a product of doing that, I'm also removing the evaporated water from the surface, right? If I'm bringing warm, dry air to that surface, then I'm also evacuating the wet air from that surface and displacing it. So my dehumidification can process it, or I can ventilate it, however we're controlling humidity. The catch here, and the more complicated factor that we just discussed, is that this happens not only on the visible surfaces, this needs to happen on all wet surfaces, whether we're talking about a wall cavity, under a hardwood floor, beneath cabinetry, behind cabinetry, inside of interstitial spaces created by built-ins, anywhere where water has migrated and wet surfaces exist. Okay, so there's a quick look at the role and purpose. Now let's take that role and purpose, and let's add to that the layer of the ANSI IICRC's S500. So hopefully, if you're on the call here today, you're familiar with the S500. If not, then that's my very first homework assignment for you, is get your hands on a copy of the S500 and become familiar with it, because this is the industry standard of care, right? It is the industry standard of care. And what is in the S500 is what we need to understand and follow and administer as professional restoration contractors, right? It not only sets us up to follow what is the right or best practice, it also sets us up to defend those practices post a restoration process. So I've highlighted here on the slide a couple of the key elements of the S500 that I'm going to talk through here today. Let's kind of break these down and digest them one at a time. The first, just S500, what is it? So the S500, even if you are familiar with it, I would encourage you to understand by definition what the S500 is. The S500 is an industry consensus standard of care. An industry consensus standard of care. And what that means is there is a group of subject matter experts that come together periodically, and they revise and update this document following the American National Standards Institute process of consensus, which means basically that a number of experts need to come to an agreement by vast majority, need to come to an agreement on everything that is in that document. And it's updated on a 5-year cycle, sometimes shorter than that. So it's reflective of the changes in our industry standard of care. There's a key word in the S500 that's used for all things that are standard of care. It's the term should, right? And the reason I want to stress this for a moment is because as we get into some of these today's topics and in future topics on this webinar, I'm going to use the word should a lot more. And I want you to understand what the word should actually means in a legal context, right? So if you as a professional, as a provider, as a practitioner, if there is a service or a practice or a procedure that you should perform, then that procedure or practice is legally binding as standard of care. And what that means is that a reasonably prudent practitioner who is trained, competent, and qualified would use that service, unless there is a documented reason for not doing so. It's legally binding, right? If you don't do it, well, you should have done it, right? And from a legal standpoint, that creates a lot of liability when we don't. So I want you to really elevate in your mind as I go through the presentation today, what the word should means. Should means that's the way we do it, right? So with that said, the calculation that is provided in the S500 is a calculation for the affected areas and surfaces within a drying chamber. And everything that I'm about ready to run through here is relevant only to affected surfaces, okay? If it's not an affected surface, if it's not an affected space, then the rule or procedure does not apply. So with that said, the first step in the S500 air mover calculation is to understand how many rooms are affected. And there should be one air mover in each affected room, right? And that's the first starting point in the calculation. That one air mover in each affected room looks something like this. So if let's take this little schematic here and let's overlay onto this, an area of migration. So the shaded area that we see, these are areas where we've gone through with our instrumentation and in one way or another have discovered abnormally wet surfaces. If we count these rooms up, there are 4 affected rooms, and the closet here qualifies as a room. So the base of our calculation, the starting point in our calculation, is that we need a minimum of 4 air movers within this space, and that's the starting point. Now, from this point forward, the rest of the calculation, and here's one common mistake made with this calculation, the rest of this calculation is done on a room-by-room basis. So the next step is that I should have an air mover for every 50 to 70 square feet of affected floor within each room. So this calculation is performed on a room by room basis. This room that I have highlighted here, for example, if this was a 10 by 10 bedroom, right, that would be 100 square feet. Then I would do the math and divide 10 by 10 by 50, right? And I would come up with 2 air movers, and I would divide 10 by 10 by 70, and I'd come up with 1 point something air movers. Round that up, and you get 2 to 2 air movers. Pretty easy range to follow, right? So 2 air movers would be required in that room. I would then start over again for the adjoining room and do that calculation all over again. And then I would do it again for the room down beneath that and do it all over again, right? So this is a room by room calculation. The closet creates a little bit of an exception to this rule, because in this rule, we do not add an additional air mover for rooms that are approximately 25 square feet or smaller. That 1 air mover we put in that room is adequate, right? So the room has to be bigger than 25 square feet for this square foot rule to apply. If you add that into the calculation, now we have a quantity room by room for the total for the floor. All right, now I'm not putting square feet up here because I don't want to go through all the math as we're going through a webinar. We just don't have time to do that today. So let's just assume that we've understood our dimensions in each room and we've applied a room by room calculation by square feet, and find that the room in the upper left corner needed 2 to 3 air movers. The wet surface area in the room to the right only needed 1. We need 3 to 4 air movers for the larger space, which is probably a bedroom in this case. And then no additional air movers for the closet, right? We had 1 for the closet. It's smaller than 25 square feet, so no additional air movers were needed in that space. So I add that to the quantity on the top of the slide. The next step is then to add air movement for the affected upper walls and ceilings. Right? Upper walls meaning that the bottom 2 feet of wall are already covered by your air movers installed for the floor. So if you have wet area that is wicked up higher than 2 feet on the wall, then we add additional air movement for that at 1 for every 100 to 150 square feet of upper wall and ceiling. In most cases, that's not what we see. So for the example here, I'm going to keep that at 0. But I do want to share with you that that is for each area of upper wall and ceiling. For example, if I had an area in the bottom right corner or the bottom left corner of this large bedroom that had migration up the wall, and that area measured 80 square feet, but I had another area in an opposite end of the room that also had migration up the wall, and it only measured 20 square feet. That's 2 separate air movers, because those are 2 separate affected areas of upper wall and ceiling. Each are going to need their own air movement to address them. This is another common kind of misconception how to apply the air movement calculation. And if you think about it practically, if these are 2 entirely separate areas that need air movement on these upper surfaces, it's going to require 2 separate air movers to address them. Okay. Once we allow for that, the final step in the air mover calculation is then to compensate for any insets or offsets. All right, these are areas that measure greater than 18 inches in their left-right dimension, right, horizontal dimension, that create an obstruction to airflow. All right, and here I've got one of them highlighted on the screen down here. The closet kind of makes an inset into the room. The length of that wall is greater than 18 inches. Therefore, it constitutes 1 additional air mover. Now, once all this is done, we then add up the total. And in this particular example, we come with 11 to 13 air movers. Okay, that's great. We've got 11 to 13 air movers, somewhere in that range. That's the recommendation being given to us by the calculation. So how do we use those? All right, how do we use those? What is best practice for the installation of those air movers? So quick summary before we get to best practice. Initial calculation only, first of all. I really want to stress that calculation that is provided by the S500 is intended to provide a number of air movers that you start the project with. It's not intended to calculate a number of air movers that will be installed for 3, 4, 5, 6, 7 days. All right. And this is another area that I think is an industry that we do need to get a lot better, is understanding that the job changes on a daily basis, right? What I installed equipment for on day 1, and then what I come back to on day 2 are technically 2 different drying problems. There should be less moisture in the building, right? Potentially even less wet areas. And as that occurs, adjustments need to be made to that installation. I'm going to give you kind of an analogy here on what I mean by this. If I start a job with 5 air movers and finish a job 5 days later with 5 air movers, all right, that means that I use 25 days of air movement, right? 5 days times 5 air movers. If that's how I progress on a job, I will not be nearly as efficient as I would be if I started with 10 air movers and finished with 2 and still used 25 days of air movement. The job would be done much, much quicker. The reason for that is because of many of the concepts that we discussed earlier in the webinar series. When we start a job, we're dealing with surface water and free water. And these are the types of water that respond well to air movement. As we get towards the latter stages of the project, we get into something called the falling drying rate. We're dealing with bound water, and bound water does not deal or respond well to air movement alone. It responds well to vapor pressure differences, which, by the way, is going to be our next topic of conversation next month, is understanding vapor pressure differences and how to leverage that. So starting heavy and finishing light on air movement is the key to effective mitigation. All right, and the more we deploy that, the more effective we're going to be. So I'm going to summarize all that and say, again, this is for initial calculation only. It's intended for just the affected surfaces. It's intended to be an initial calculation. We should be adjusting as the job progresses. And it only addresses the standard air movers, right? This is the air movement required for those visible spaces that we're seeing within the affected area. It does not deal with the interstitial cavities and interstitial pockets that also need to be dried. Those are specialty air movers, and we'll address those separately. Okay. All right, so now let's move into how we install these general air movers. Once I know how many I've got or how many I should be using, let's talk about how these would best be deployed. Okay. Good reminder here, by the way, I see some questions already coming into the Q&A area. Make sure you drop those in there. A special thank you to Kirk and Thomas for getting those in there, and I'll address those questions as we hit the end of the presentation. So installation best practices, what does that look like? Let's go back to a little bit of a schematic here and talk about how air movers would be deployed in this space now that we know how many. The first air movement I want to start with is there to achieve a very specific purpose. All right. And that is to ensure that within these 4 rooms that we're dealing with within our drying chamber, that the temperature and humidity in each of these spaces is going to be well exchanged. All right. But I'm going to circulate air between all of these rooms so that it doesn't matter where my dehumidifier goes. All right. I don't want a dehumidifier in every room. Right. That would be impractical, especially in something like a closet. Right. Dehumidification shouldn't matter where you install it. It should not matter where you place it. There's some places I wouldn't want to put it, like on top of a hardwood floor if I can avoid it in case the dehumidifier leaks, or right in front of an air mover so I'm blowing air at the front of the dehu. So there's some places I wouldn't want to put it. But aside from that, it shouldn't matter where the dehumidifier goes. If I install my air movers properly, then no matter where the dehumidifiers are in the chamber, I'll be mixing that air throughout the space and getting a balanced condition throughout the chamber. So to accomplish that, I'm going to start with an air mover type that does something very, very specific. And there are 2 types of air movers that do this. To understand that, let's take a top-down look at this air mover. So we're looking at the top of the air mover, and we see the handle there, that straight line across the bigger barrel of the air mover, and then the snout, the outlet of the air mover down at the bottom. This type of air mover has an outlet in the front, and it has an intake on the side. Notice how this air mover bends the airflow 90 degrees. This is critical, all right? It's got a correction to the airflow of 90 degrees. And there are 2 types of air movers that do this. The air mover you see pictured on the screen, something we call the centrifugal air mover. That's the technical term for it. You may call it a carpet dryer, a turbo dryer. Just don't call it a fan, right? And if you don't understand that conversation, we'll save that one for later. Never call them fans. But this centrifugal type air mover does this. The other one that does it is the low profile air mover. And I'll show you a picture of that here in a second, but that's that newer kind of more flatly oriented air mover. It also bends the air 90 degrees. Either one of this will do what I'm about to show you, either one of those 2 types. That type of air mover is going to be installed at the opening between 2 adjoining affected spaces. So, and there's a few of those openings between adjoining affected spaces in the schematic. I don't care which one you start with. Just pick an opening between 2 adjoining spaces. Now, notice what this air mover does. Its intake is drawing from the larger bedroom. Its exhaust is blowing into this, I don't know if it's a walk-in closet off of a bathroom, what that is, but it's drawing from one affected room and then exhausting that air into the next affected room or space. Now, this air mover is blowing air at like 1,000 cubic feet per minute. Maybe even 1,200 or 1,300 cubic feet per minute. And depending on the size of these rooms, what that translates to is the air is going to be exchanged back and forth between these rooms about 60 times an hour, or 60 times a minute rather. That's a really, really high rate of exchange between these two rooms. And it doesn't give these rooms any choice but to be the same temperature and humidity. I could put the dehumidifier in a small room. I could put it in the big room. It wouldn't matter because of the rate of exchange blending the air between these two rooms. Now, once that first air mover is installed, continue to do this between each affected room. So again, here down in the closet, I would do the same thing. At this opening between this larger affected room and the closet, I'm going to install that air mover so that it draws from the larger room and then forces that air into the smaller closet. Again, creating an air exchange between these two adjoining affected areas. Now I'm going to pause there for a minute. Because of how these air movers are designed, if you're standing above the air mover, taking a look at it, that intake is only on that right-hand side that you see on the screen, all right? And the exhaust down at the bottom. That's where the intake is, regardless of manufacturer. It doesn't matter who made the air mover. They're all the same. That intake is on that same side and the outlet is always in the front. So the only way to make this exchange work across all these openings between adjoining rooms, believe it or not, is to install them in a clockwise orientation. And there's been the debate in the industry for years. Do I blow air movers clockwise around a room or do I do it counterclockwise around a room? I've even heard somebody try to justify it by which direction the water goes when they flush a toilet. Honestly, it doesn't matter except for this reason. This is the only reason why I will tell you it needs to go clockwise. Because if I go counterclockwise, I'm not going to create the exchange between rooms that we need to create. So always go clockwise to make sure the opening is drawing from one room and then dumping into the next. Okay. Now, once these two air movers are installed, that was only 2 out of the 8 to 11 air movers we needed. Where do the rest of them go? Right. So the rest of them are going to continue that airflow around the perimeter of the room. And for this, I can use a number of different types. At the top of this image of air movers, you see the low profile type air movers. These are great because they have really good energy efficiency, which to me is probably the #1 limitation to that initial air mover installation, is that if you're using air movers that aren't very energy efficient, in many cases, you're going to run out of power availability for what you need for that first 24 hours of drying. So using something like a low profile air mover where you're getting 1,000 CFM for only like 1.5 amps, somewhere in that neighborhood, is a really, really good use of energy that's available inside the property. It can run a lot of air movers on a circuit that way. The traditional centrifugal air movers are like 5 amps for the same amount of airflow, right? So you're using more than twice the power and only really giving you about that same amount of airflow, maybe a little bit more, but not a lot, not measurably more. And then you've got axials, that's the lower left-hand air mover that you see there, which is also extremely energy efficient. For about 2 amps of power, you're getting a couple thousand CFM. They're the most energy efficient type of air mover. And you can call those fans as long as you put axial in front of it, right? And call them axial fans, not just fans. So anyway, I can use any of these types to boost the airflow. From an energy efficiency standpoint, the axials are going to be your most energy efficient. Your low profile air movers are going to be your second most energy efficient. And then your centrifugal, that traditional air mover, I'll use it if I need to because it works, but it would be the least energy efficient choice. So I'll take these air movers, I'll drop them in along the wall and boost that air movement along the perimeter of that wall assembly. Okay. I'm going to move them in the same direction as the air movers that are creating the circulation room to room. And that's critical. I want the air movers to all work together to move this air through one space and into the next, and then through the next space and into the next. So to illustrate this, I'm going to grab my mouse and put my mouse on screen here. And let's just start with this first air mover that we installed. And note that as I move the exhaust from this air mover, if I move in this clockwise direction, I'm continuing this flow all along the perimeter of this room, right? So that ensures that this air moves through the entire space before it jumps back out the door again. Let's start down here and again, follow from this first air mover through and around the entire space, then into the neighboring room, and then through and around the space of the neighboring room. You're basically using the wall assemblies. Here's a good way to kind of think of this. You're using the wall assemblies like a duct system, right? Where I'm moving the air along the walls as though they are a transportation system to move and circulate that air through the entire footprint of my drying chamber, right? That'd be another really good way to think of how strategically we're trying to place these. Now we're almost done with the general air movers, almost, not quite though. When we take a look at some of these bigger spaces in these bigger rooms, especially when we've got a lot of contents, let's say this was a bedroom and we've got, a bed, we've got a dresser, we've got a nightstand, we've got a desk, and we've pulled all that out away from the perimeter so we can get this perimeter airflow. That's great for the perimeter, but what about the middle of the room, right? I still need to dry out the middle of the room. So that those contents, if they're being restored on site, which generally speaking, they should be dried on site unless there's a reason why they can't, then we would go underneath those furniture items, make sure that they're blocked up with some foam pads, get an air break underneath there of at least a couple of inches of height. And out in the center of the room, we would deploy these axials in a downward flow, right? And that's going to ensure that we not only get airflow out in the middle of the room and cover that middle surface, but we also get air along the base of those contents that were at one point in contact with the wet floor. So we're getting kind of a double exposure or double benefit out of that air movement out in the center of the room. All right. So there's best practice on installation, the best way to put in our general air movement. I want you to also note, however, that as soon as these air movers are deployed, you should verify that these air movers are properly moving air along all of the wet surfaces. And there are two ways to test this. One way is the hygrometer test that we've already discussed at length in previous episodes. And that is just making sure that the air at chest height is the same as the air down at foot height. Right? Same temperature, same humidity. If you find areas within that affected space where the floor is substantially wetter or cooler than the air at chest height, your air movement installation is not doing the job. Right? Either an additional air mover is needed, some adjustment on angle of air movers is needed. Continue to adjust until you get an equal condition at both of those levels. Now, taking 100 hygrometer measurements is not practical. And that may be the first thing that popped into anybody's mind who's used a hygrometer as soon as I said that. So taking lots and lots of hygrometer readings is not going to be practical. So take a couple of hygrometer readings to validate that, but you can also use your hand, believe it or not. What you're looking for is sensible airflow at the wet surface, sensible airflow. And sensible airflow, that means that your hand is going to feel the effect of airflow because of the byproduct of evaporative cooling, which is exactly what you're trying to do to the wet surface. If there's enough airflow to make your hand feel cool because the moisture is leaving your hand as air moves across it, then you have the effect of evaporative cooling. There is enough airflow to remove the sweat, the evaporating moisture from your hand, and create that sensible cooling as that moisture and energy leave. So at a minimum, at least check with your hand and make sure you've got that sensible airflow underneath those contents, across the middle of the room, in all these nooks and crannies, in and around these corners where it's difficult to get the airflow, in and around these obstacles and insets, et cetera, et cetera. And if there isn't sensible cooling, or if you want to get really precise, if there isn't the same temperature and humidity as you would get chest height down at the floor with a hygrometer, adjust air movement, install air movement, continue that process until we can validate that there is air moving across all wet affected surfaces. Okay. And this is key. This is critical. It is standard of care to ensure that you have air movement across all wet evaporating surfaces. That comes right out of the S500. You must have that in your initial installation. If you do not, then here's what's going to happen, right? All the surfaces that have it, they're going to dry well for the first 24 hours. But the surfaces that aren't going to dry well for the first 24 hours. In fact, they're going to get wetter, right? All that surface water and all that free water sitting in the pores and openings is just going to continue to absorb. It's going to go deeper into the assembly. It's going to go deeper into the plywood substrate. It's going to go deeper into the slab on grade, whatever it is, it's going to absorb deeper. And that additional 24 hours of absorption is going to add 2 or 3 days to the drying process, because now I've got to dry deeper into those assemblies. You just went from a class 2, right, which is relatively easy to deal with. And if you don't follow classes yet, another homework assignment for you, but that's basically describing where the water is and how much is present. You're going to go from a class 2 to a class 4, right, which is difficult. It's challenging, right? It's specialty drying. So I have to address all of these surfaces initially. If I don't, those areas are going to get worse in the first 24 hours. Those are the problem areas you end up dealing with on day 4, day 5, day 6. Those are those problem areas, the ones that didn't get addressed with air movement on day 1, right? And again, I've said it before, I'll say it again. It doesn't matter if I dry 90% of this job in 4 days, if 10% of it takes me 7 days, right? How long did the job take? It took 7. Nobody cares about the 4, right? It's going to take the 7, right? So it's important to make sure that we give everything equal opportunity to dry, right? So anyway, I've beat that topic as hard as I can beat it for today. We'll move on. All right, so installation best practices. Quick review of some of those best practices. First of all, the goal here is to get full circulation of airflow onto and across all wet evaporating surfaces. That's the goal, right? I gave you 2 ways to verify that, as simple as using your hand to feel that sensible cooling from that air moving across it. If you want to be more precise or give yourself some really good documentation, then use your thermal hygrometer at that surface, especially in higher value surface materials or projects where we're dealing with higher value goods. It'll be worth that time and energy to take some of those measurements. If you feel you need to add additional air movement, it's a great measurement to document the justification for adding that additional measurement, because it puts numbers to paper. I can document the humidity was too high at that surface. There wasn't enough airflow. I can add the air mover, take the reading again and show that corrected it, right? So it gives me great documentation. All right, so full circulation. Begin at the opening between affected rooms. That's where your first air mover is going to go. Clockwise direction, air mover that bends the air 90 degrees, draws from one affected space, delivers air to the next affected space, right? So that's how we begin. Use centrifugal or low profile air movers at those openings because they give you that 90-degree bend, right? That's the reason why we're going to use those. But then for boosting airflow, try to really maximize the electrical efficiency you get from axials. So the rest of that air movement, they could be low profile, they could be axials. I would lean you towards axials because you're going to have the best opportunity for the amount of airflow versus the power consumption. But low profiles are really good at that too. They're also very, very energy efficient. What I would steer you away from is using that traditional air mover for all of this because you're going to run out of power very, very quickly if you do. Okay. All right. So that's installation best practices. And again, a reminder, questions on any of that, drop them into the chat. Now let's talk a little bit about specialty systems. Okay. And again, episode 7 is going to dig real deep into these. So I'm just going to give kind of an introduction to the topic here today. We're not going to dive super, super deep, but because this is a component of air movement, I do want to at least ensure that we're putting this on our radar today. So what do I mean by specialty systems? So there's lots of different air movers out there that don't just produce a lot of air. They also do so well under resistance to airflow. They have a lot of what we call static pressure, the ability to force air to move through restricted spaces. And we have a lot of restricted spaces that we need to dry, right? Whether we're talking about wall cavities or hardwoods or cabinets or built-ins, whatever it is. The variety of these systems are all a different balance between the amount of air they produce and the pressure that they're capable of producing behind that airflow. All right, so it's a balance between the two. And generally, those that produce more air don't have quite as much pressure. And those that have a whole lot of pressure to force it through really tight spaces, well, they don't produce a lot of air. So it's usually a balance between these two, okay? If we had a whole lot of both, then you would need a 230-volt power source to run the air mover. So it's got to be kind of a balance between the two. Understanding when these systems are necessary means that we need to, again, understand what are we dealing with for affected surfaces? Where is the water evaporating? Right? And is that water evaporating in hidden, trapped, or otherwise, covered areas or spaces throughout the project? For example, is the water evaporating from the back side of a multi-layer wall assembly or from the wall plate inside the assembly because we had standing water or water running down through the wall cavity itself? Or is the water evaporating in the decking material beneath the hardwood floor? Right, trapped underneath the hardwood itself? Or is the water evaporating behind or underneath a set of cabinets? These are all spaces that a general air mover is not going to address, right? That one for every 50 to 70 square feet, that one per room, that one for every offset for upper walls and ceilings, those are not addressing these spaces. So the use of air movement in these is above and beyond those calculations. So these spaces, if they are wet, I'd highly encourage that you have good documentation showing that they're wet. And then secondarily, we need to assess what is the most economical way to move air through this space, right? And generally speaking, the higher pressure systems are going to require smaller openings to get the airflow into those spaces. The lower pressure systems are going to require larger openings, right? To the extent that we may be talking about openings that are 1 or 2 inches in diameter for really low pressure systems. Those would be things like taking your general carpet dryer and using an adapter on that with vents, right? Those are really low pressure systems with good airflow, but really big openings are required to get that air to move into those spaces. All the way through to systems that are producing 100 inches of static pressure or more that are capable of delivering air through holes that are a fraction of an inch. right? And again, when we get into episode 7, I'll dig pretty deeply into some of those different types of systems, best ways to install those systems, how to monitor those systems, how to adjust them. So we'll dig pretty deeply into that in episode 7. So those, just kind of a quick introduction to these specialty systems, a quick review of some of those concepts and specialty systems. First, the rule is we need to inspect, right? We need to know if those wet surfaces are present, that are hidden, trapped, or otherwise, out of sight inside of an assembly. If those surfaces are present, then we need to identify where those surfaces are in the cavity and then assess the best way to get airflow along those surfaces. What's the best route of access so that I can get air movement across these surfaces? A couple of other just real quick side points in that, by the way. Be very cognizant of contamination, hazardous materials, building code requirements in your particular area of operation. As soon as you start to manipulate wall assemblies, cavities, et cetera, to make access for airflow, just be aware. It may or may not be required that you do some asbestos testing before you do that, depending on where you are. If you're dealing with a structure that has some previous water damage, there may be some microbial growth in the cavity. So be cognizant of contaminants as soon as we start manipulating spaces that we can't see or manipulating building materials directly. Okay, so just be aware of that. All right, so that gets us through the major concepts. Now I want to kind of start wrapping this into a review. And this is my last reminder. Make sure we get questions into the question area. So I'm going to hit those here in just a few minutes. So quick review, maximizing the air movement resource. Rule number 1, air movement must be at the surface. Okay, I can't stress this hard enough. I've made sure that in every one of our episodes to date, we've had an opportunity to throw this concept back out there. But if the air does not reach the wet evaporating surface, then the air is doing no work for you, right? It is the air in contact. I've heard it communicated as it's the air that communicates with the surface, right? It's in communication with the surface. And I like that phrase, but it has to be in contact. Measure for it, feel for it, validate it, document it, make sure that air is happening right at the surface. Also with air movement, it's room-to-room circulation that we start with, right? So that first air mover that you're going to put in a drying chamber, the reason it's there is to mix the air on a horizontal plane and make sure that horizontally we have the same conditions throughout, right? Then we'll install the air movement to make sure that vertically we're getting down on all of our surfaces. Leverage the axial electrical efficiency. With air movement, I want you to start heavy and lighten up as you go. Right? But the only way it works to start heavy is if you lighten up as you go. Don't follow the S500 recommendation or calculation for air movers to come up with 30 air movers in a property and then leave all 30 air movers there for 7 days. That's not practical. You do not need 30 air movers 7 days into a job. You probably needed them on day 1 if that's what the calculation said. But as you move through the process, you should be reducing the number of air movers. That is the right way to dry a structure. Okay. Leverage axial electrical efficiency, we just said that, and identify all of the hidden wet surfaces, right? It's not just air movement across the carpet that you see. It's the air movement across all of the interstitial cavities and voids and the surfaces therein that also needs to be established if those surfaces are wet. If water comes from overhead, you have standing water in a space. If either of those are true, or the water source was inside the assembly, then you have wet surfaces inside those spaces. Right. And in those cases, we need to inspect, we need to identify what's wet, and we need to get the air movement on all of those surfaces. Okay. All right. So those are the concepts that I wanted to run through here today. We got about 15 minutes remaining, plenty of time to get into the Q&A. Before we do that, I'm going to stop the recording here in just a minute. And as I do that, I want to make sure that I capture a couple of things in the recording. So bear with me a minute before we get the Q&A started. First of all, this was episode number 4 of Technically Speaking, Maximizing the Airflow Resource. Again, my name is Brandon Burton, Technical Application Vice President at NextGear and CoreLogic. And here's a quick look at our agenda coming up for the rest of the year. We just covered off on episode number 4. So next up, episode number 5, all about vapor pressure. If you just want to really geek out with me on psychrometrics, right, and really satisfy the need to get really deep into the nerd world of vapor pressure and psychrometry, which I love to do, definitely join me on the next episode. Okay, and that's going to be in May. Episode 6 after that, we get into humidity control. And then in July, as I'd hinted at, we're going to get really deep into interstitial cavities and cavity drying. So just mark your calendar for those upcoming episodes. and make sure that you're here, especially if those pique your interest. And with that, we will wrap up the recorded part of the session and we will jump into Q&A.